Hi, this is ET370, lecture 12, and we're going to talk about binary and 2's complement, and this will be a two-part lecture. So the second part, we'll talk about floating point. Okay, so in this first part, we're going to go over addition, subtraction, and then we'll look at a way to represent negative numbers, because that's going to make our subtraction easier by adding a negative number. We'll talk about the max range and some issues like overflow and underflow. All right, so let's begin. So binary addition, let's do a simple problem. If we just take 7 plus 3, we're going to get 10. No problem, right? Decimal. But let's do that same math in binary and see if we get and circle around to the same result here. So if we take 3, that should be 1, 1. Remember, 1's place, 2's place, right? You're going to get 1 plus 2 is 3. And 7 should be 1, 1, 1 because you have the 1's place, the 2's place, and the 4's place, right? So 1 plus 2 plus 4 is 7. Okay. Now, if we add this up, let's see what we get. We get 1, 1, 1 plus 1, 1, and 1 plus 1 is 10. Good. 1 plus 1 plus 1 is 11, right? Because it's 10 plus 1, 11. And then a 1 plus 1 again is 10. So you get 1, 0, 1, 0. Okay. Now, 1, 0, 1, 0, does that match what we would expect for 10? Okay, so what do we have? 1's place, 2's place, 4's place, 8's place. 8 plus 2 is 10. Yep, 8 plus 2 is 10. Good. So you can see that just straight up adding the binary, whether it's in binary or it's in decimal, you're going to get the same mathematical result. Okay, so let's look at subtraction, right? And I'm going to just say it right out of the gate. It's a little bit annoying because you got to deal with carry and borrow. Okay, and so if you have, for example, 8 minus 3, we know that's 5. We can convert everything to its equivalent binary. 3 is 1, 1, 8 is 1,000, and 5 is actually 0, 1, 0, 1. And let's just double check that. 1's place, 2's place, 4's place. Good. 4 plus 1 is 5. Good. And so let's confirm that this is true, right? So we're going to take 1,000 minus 1, 1, right? So let's see what we get. So if we take 1,000, right, minus 1, 1, what do we get? We get, well, we see all the zeros, right? So we gotta borrow, right? And so what do we have? This 1 goes over here, right? And you're like, oh, that's so annoying. But then eventually you're able to get what you want because now you have a 10 here, minus 1, which is 1, 1 minus 1, which is 0, 1 minus 0 is 1, and then this guy, sorry, is gone, right? So we had to borrow all the way over here from the, the 8's place, okay? Over here, we get the answers 1, 0, 1, and does that match? It does, but it wasn't so fun, right? It wasn't so fun. So let's introduce a way to deal with negative numbers. And actually, that's called 2's complement. And if you remember, 1's complement is just flipping the bits, right? 2's complement is going to be flipping the bits plus something else. Because if you can represent things with 2's complement or negative numbers, you can still use that original addition here, which is super easy. You just add 2 numbers, okay? So that's the story. Now, let's look at this 2's complement for negative numbers. What do we have to do? The first thing you have to really know is how many bits are you going to use? That's so important. You really need to define the number of bits first and foremost, okay? Now, the total number of unique combos is still 2 to the number of bits, so that doesn't change, right? Now, the max positive number is now no longer 2 to the bits minus 1. It's 2 to the number of bits minus 1 minus 1. And why is that little minus 1 there? Because it's going to cut it in half, right? And this is to count for the 0. Now, what about the minimum negative number? It's negative 2 to the number of bits minus 1, okay? All right, now what's the process? The process is super easy. You're going to invert the bits, which is what we call 1's complement, and then you're going to add 1. That's it. Super easy process for 2's complement. Okay. All right, so let's look at an example of this. Look at the range for 4 bits. Like I said, we have to define the number of bits. So let's say we're in a 4-bit world, which is a nibble, and we're in 2's complement, and we want to calculate, well, what's the maximum positive range for 2's complement? Well, we're going to use our formula, 2 to the number of bits minus 1 minus 1. So that's going to be 2 to the 4 minus 1, which is minus 1, which is 2 to the 3, which is 8 minus 1, which is 7. Okay. Well, what about the minimum negative number? Well, negative 2 to the number of bits minus 1, which is negative 2 to the 4 minus 1, which is negative 2 to the 3, or negative 8. So the range goes from negative 8 to 7. Notice it's a total of 16 numbers. Okay? Now, we've seen this already before, right? We've seen 0, 1, 2, 3, all the way down to 14 and 15, right? Okay, maybe I'll do it like this. Maybe I'll do 0 through 15, okay? So this is 4 bits. But now with 2's complement, what are we seeing? We're seeing from all the way down to negative 8, all the way to 7. So you see we're getting the same number of unique combinations, which is 16 in this case, right? 16 numbers and 16 numbers. But what 2's complement is going to allow us to do is shift this all the way over and represent some negatives here, okay? All right, so let's keep going. So let's write it out. Okay, let's do some quick examples of 2's complement. So if I have 2, which we know is 0, 0, 1, 0 for 4 bits, what is negative 2? Okay, so we're going to use that process. Invert, which is 1, 1, 0, 1, and add 1. 1, 1, 1, 0. If I add 1 here, I get 10, right? So this is actually the equivalent of negative 2. All right, so negative 2 base 10 is 1, 1, 1, 0. Okay, now how can we check? Can we see if we add these two numbers, do we get 0? Let's double check. So we're going to take this number plus this number and see if we get 0, right? So 0, 0, 1, 0 and 1, 1, 1, 0. So what do we get? 0 plus 0 is 0. 1 plus 1 is 10. 1 plus 1 again is 10, and 1 plus 1 is 10. Now, here's the reason why defining 4 bits or the number of bits is so important, because look, I have an extra 1, but I'm going to ignore it since I'm only using 4 bits. And check this out. I get 0, 0, 0, 0, which is matching our intended result. Okay, so good. This is highlighting how we can first get 2's complement, and how do we use 2's complement, and why the number of bits is so important. Okay. Let's look at our table for 2's complement 4 bits only, right? Okay, so over here, what I have is the normal binary 0, 1, 0, 0, 0, 1, 0, 0, 1, 0, 0, 0, 1, 1, 0, 1, 0, 0, 0, 1, 0, 1, 0, 1, 1, 1, 0, 1, 1, 0, 0, 1, 1, 1, and 1, 0, 0, 0. This is great, okay? Now, if I want to build the 2's complement, for example, of these positive sets of numbers, let's do it. So for 1, what am I going to do? I'm going to invert and add 1. Okay, so look at this, 1, 1, 1, 0, good. And I'm going to add 1, so I get 1, 1, 1, 1. That number is going to go right there. Okay, let's do it for this one. For 2, we actually just did it for 2 already, so we should get the same result. Yep, 1, 1, 1, 0, that's the same one here. And that's going to go to the next one here, 1, 1, 1, 0, perfect. What about 3? I think you guys can predict it. 1, 1, 0, 0, good. And then plus 1, 1, 1, 0, 1, and that's going to go here, okay? And so on and so forth, right? 1, 0, 1, 1, 1, 1. If I add 1 to here, I get 1, 1, 0, 0. It's going to go to the next one, good. And then what's next? 1, 0, 1, 0, good. 1, 0, 1, 0, everything inverted, plus 1. 1, 0, 1, 1, good. It's going to go up there, excellent. 6, right? And then this is negative 6, okay, which is 1, 0, 1, 0, good. 7, so I get 1, 0, 0, 0, and I add 1, 1, 0, 0, 1, good. And the last one, 8, right? Invert plus 1, okay, here. Now notice, I don't get to use positive 8 for 4 bits, right? This is out of the range, in fact. So look at how 1, 0, 0, 0 kind of came back on itself, right? So this is very important to realize. If we go back to that maximum range, we had 2 to the number of bits minus 1, right? This one is to cut it in half. This one is to count for the 0 here, right? So that's why you don't get to include this 8, okay? All right. This is a table of 2's complement for 4 bits. Now you can do 2's complement for 8 bits. You can do it for 32 bits, but you do need to know the number of bits here. Now, what is the problem with 2's complement? I think you can already see it here. It's going to be overflow and underflow. So let's say you're doing some computation and the computed number is greater than the maximum positive number, right? Let's say you're trying to add 4 plus 4 with a 4-bit. You're going to get 8, but what's it going to spit out? It's going to spit out -8, right? That would not be good. That's an overflow problem, right? Same thing with an underflow problem. If you were trying to add -5 plus -5 and your expected result is -10, you're underflowed. You're out of the range of what you can do. Okay. All right. So let's do a simple example, some more examples, just to kind of hit this concept home. So let's say we have 4 bits, 2's complement, and we want to see if 7 plus 7 gets 14, right? And I think we can already see that this is going to be a problem, right? We're going to be way past our limit. This is definitely going to be an overflow, right? But let's just confirm and see what we get. So we're going to say, what's the number? 2 to the number of bits minus 1. We already know that this is going to be 7. That's less than 14. So this is actually not good, okay? And then let's just see what happens. So what is 7? This is 0, 1, 1, 1. Good. Okay. And let's just double check. 1's place, 2's place, 4's place. Yep. Good. And I'm going to take these two and add them together, right? 0, 1, 1, 1 plus 0, 1, 1, 1. So I get 10, 11, 11, and what do we have here? 1, right? Good. Okay. So now look, I just want you to note this. If you see a 1 here, that must be a negative number. Check this out. All these numbers with 1s are negative, right? That's the pattern. So if you're in a 2's complement world and you see a 1 on what we call the most significant bit or the leftmost bit, that means it's a flag saying, I'm negative, I'm a negative number, right? Okay, so we know that that's definitely not going to be positive 14, right? So what number is this, right? What is 1, 1, 1, 0? Well, if we look on the table, 1, 1, 1, 0 is actually -2, right? And if we didn't have the table, could we actually convert this? If we know this is negative, could we convert it back to the positive number? We could apply 2's complement again. So how do we do that? Invert and add 1. So this becomes 0, 0, 0, 1 plus 1, and you go 0, 0, 1, 0. So this is the positive result, and you can see that that's +2. Okay, so what happens when you have 4-bit 2's complement and you add up 7 plus 7? It'll spit out -2, not 14. Okay. All right, let's do an underflow. Do we do an underflow example, or do we just do another example? Oh, we just do a different example. 5-bit 2's complement. Okay, so let's say, is 13 minus 6, is that going to be okay? We expect to see 7, right? Is that going to be within range? Okay, so we're going to check it. Maximum positive number, it's 2 to the 5 minus 1, so 2 to the 4, which is 15 minus 1. Okay, so that's good. Okay, all these numbers are all good. What about the minimum negative? So that's going to be -2 to the 4, which is -16. All these numbers are within -16 to 15. Yeah, I think we're good. So now we can go ahead and crunch this. So if we have 5 bits to ourselves, 5 bits available, what's the binary number? 0, 1, 1, 0, 1. Let's double check. 1's place, 2's place, 4's place, 8's place. So this is 4 plus 8, that's 12, plus 1, that's 13. Good. What about 6? 6 itself is going to be 0, 0, 1, 1, 0. So what is 1, 1? So 1's place, 2's place, 4's place, that's 6. Good. And remember, I'm subtracting, so I got to apply our 2's complement to get the negative number. So I get 1, 1, 0, 0, 1 plus 1 to get 1, 1, 0, 1, 0. That's going to be our -6. I can add these two. Okay, and so what do I get here to add? I get 0, 1, 1, 0, 1, good. 1, 1, 0, 1, 0, good. And so I'm going to add 1, 1, 1, 10, 10, and I'm going to ignore that bit because it's beyond the 5 bits. And look at this, 0, 0, 1, 1, 1, that is 7. That matches our answer. So this is an example of 2's complement with 5 bits. And once you get an answer, you truncate off anything beyond the number of bits you're using. Okay, I hope this lecture helped a lot, and I look forward to see you in the floating point part.